Alrighty.
All right.
Yep, K8AMH. Welcome back to Mentorfest. All right, let's go ahead and officially kick off our next session here on Mentorfest 2021. Aaron Kilo 8 Alpha Mike Hotel here, switching it over here for our space weather for hams, which is something I'm looking forward to learning more about. So with us is Stan NW5Q, Quebec is going to tell us more. So Stan, over to you.
Okay, great. Thanks, Aaron. And thanks everyone for joining me today. I am Stan NW5Q. And I think it's interesting. No one seems to be sure what this presentation is about, so I guess I'm good. I guess I would say that maybe Monty Python would say, now for something completely different. You've had a lot of good presentations so far, and they've been pretty detailed. This is a little more abstract, but I think it's an important topic, and I will definitely tie it down here when we get to the end. So let's talk about space weather and its impact not only on hams actually, but it actually impacts all of us. If you have a cell phone, if you use GPS, space weather can have an impact on you, and it may well in the future as we get more involved with technology. So, but it's especially important for those of us that play on HF. So to just start this out, let's talk about HF itself, and let's say, you know, uh, why do we get on HF? Well, we usually want to see how far we can talk. That was the reason I got on HF. And you get your new radio and your first antenna, and you want to see who you can make contact with. And before you know it, you're usually chasing some kind of an award. Countries, states, counties, parks, summits, you name it. If there's something out there to collect, people will collect it. And as you start that pursuit, you quickly figure out that line of sight or ground wave propagation is not going to cut it. So you need ionospheric propagation. And as we know, ionospheric propagation is because the ionosphere refracts some radio signals. Now, the more energized it is, the higher the refracted frequencies. So if it gets really energized, 10 meters open, 6 meters opens, life is good. Well, you have to realize the ionosphere is almost totally energized by the sun. So let's examine just how that happens. Let's talk about space weather. Now, what is it? Okay. Space weather is really nothing but about the sun and its impact on our entire solar system. But most specifically, of course, we care about Earth, and that impact is via the solar wind. And the solar wind extends all the way out through the solar system, well beyond Pluto, actually. The sun has that much effect. So let's briefly talk about the sun. Okay, we need to realize the sun has a strong magnetic field, and the sun rotates about once every 27 days. Now, the sun is the plasma. It's not solid. So it rotates slower at the poles than it does at the equator. So at the equator, it rotates about once every 24 days. And at the poles, it's more like 35 days. So 27 is kind of an average. But as you can imagine, with this massive thing rotating at different rates and magnetic fields all over the place, eventually these magnetic fields get very twisted up. If you twist a spring far enough, eventually it snaps, right? So when you twist it, it becomes unstable. And that's where things happen. So here's just a depiction of the sun's magnetic field at one point in time. And as you can see, it's kind of a jumbled up, tangled up mess. And these lines get all tangled up and intertwined, and weird things happen, at least as far as we think about things. But it's really a complex system. And it generates the solar wind. So what is the solar wind? Well, it's not a wind like you think of in normal terms here on Earth, but it's simply a high velocity stream of charged particles. There are a lot of ions, protons and electrons and just energized molecules. And the sun generates that solar wind continuously and in all directions. But we only really care about, of course, the side that faces us. Now, the solar wind also transports the sun's magnetic field, and that is known as the interplanetary magnetic field, or IMF. You may, if you read some scientific papers or something, you may see it also referred to as the HMF, the heliospheric magnetic field. But most of the stuff amateur radio related that I've seen refers to it as the IMF. And that solar wind, like I said, propagates throughout the solar system, well beyond Pluto even. So there are a number of events that happen on the sun, and it's a very active place most of the time, although it's been pretty quiet here of late. But we're only going to talk about a few things. We're not going to get into any details here. We're not trying to be solar physicists. I just want to give you some background. So we talk about a few factors, we can have some understanding, some basis for it here. So events and disturbances that are on the sun, that are on the side that faces the Earth, can definitely affect us. And we're going to explore 4 such events just at a high level. One of them, of course, is good, and 3 of them generally not so good. And that, when I say good and not so good, that's in terms of radio propagation, not so much serious events, but just radio propagation. So let's talk about the good one first, sunspots. So you've probably heard people talk about sunspots. Even if you're a new ham, you've probably heard references because there's a lot of interest right now. But you need to understand that sunspots are areas of tightly closed magnetic fields. I mean, virtually nothing is going to radiate from a sunspot. It's that tightly closed. The interesting thing is that the areas around them are highly active, emitting X-rays and extreme UV light. Now, you need to also understand that extreme UV light is what energizes the ionosphere the most. So sunspots actually are a really good proxy for solar activity, and also a good proxy for how energized the ionosphere may get. So we track sunspots closely, and we have for a long time. Sunspots are cooler than the surrounding area, so they appear dark if you look at a photo, which I'll show you in a minute. But they're still about 6,500 degrees Fahrenheit. You wouldn't want to spend a lot of time there if you could, but the surrounding area is more like 10,000 degrees, so it's a little bit cooler. You may have heard about the sunspot cycle. That's an 11-year cycle where, you know, we start out with no sunspots, we reach a peak, and then we drop back down to minimum again. And this takes roughly 11 years. It has varied anything from 10 to 14, but as a general rule, it's 11 years. When the cycle starts, the sunspots for the new cycle start appearing at roughly 30 to 45 degrees latitude, both north and south on the sun. And over the course of the cycle, they migrate toward the equator. And we have really just started solar cycle 25. Solar cycle 24 was officially declared ended December of 2019. So we're just a little over a year into cycle 25. And here it's just showing you sunspots. These dark regions on the sun are sunspots, and they typically cluster in groups. And while nothing emits from the dark spots, everything around them can be very active. So we like sunspots. The more, the better. Right now we have, last I checked, we have 29 sunspots, or at least the number is 29. And we've had a little bit of activity. So that's good. We went a long time without seeing a sunspot. So the more, the better. Now it's also talking about these other less favorable solar conditions. And when I say less favorable, I really mean for radio propagation. They're not necessarily less favorable for other things. For instance, the first one we're going to talk about is coronal holes. Now, these are literally holes in the corona of the sun that expose the inner regions. And they usually result in an accelerated solar wind to make the wind faster. And aurora watchers and photographers love coronal holes because they are typically the cause of aurora. Unfortunately, they also often disturb the ionosphere, so we're not so happy about them. But if you're in a position where you can see auroras, it's quite an exciting thing to see. So we have coronal holes, and now we have the two that frustrate me. If you look at uh, news articles, press reports, reports of something coming at us, they always confuse these two, and they're very different. So first of all, let's talk about solar flares. Solar flares are bursts of radiation, and they're usually around a sunspot region. They release a ton of X-rays and radio bursts, may cause radiation storms, and they can also cause radio blackouts. Now, we don't have to worry about radiation storms. The radiation storms are where there's a ton of energized particles. We're protected here on Earth, but it is important for astronauts. And it's going to be even more important as we start to transition to the moon or even Mars. If you get caught out unprotected in a major radiation storm, it could kill you on the spot. So that's going to be a real concern for those efforts when they get underway. They can also cause radio blackouts. And I don't know if you've ever experienced a radio blackout, but it's an interesting thing. All of a sudden, you really can't talk to much of anybody except your neighbors. The band just died. And I mean, that could be 20 meters in the daytime, which would normally be hopping, and suddenly it's just dead. So that's not a good thing for us. But these are fast. They travel at nearly the speed of light. So we don't really have any warning for solar flares. By the time we know that we've had a solar flare, it's here. And they rate the intensity of them from A, B, C, M, or X. So A, B, and C are pretty moderate. In fact, we just had a C solar flare here a couple days ago. Haven't seen any M or X class ones yet. The X class ones are the serious ones, the ones that really can cause damage. We hope we don't see many of those. So a lot of times along with solar flares, we get a solar storm that follows it. And a solar storm is really a coronal mass ejection. You may have seen the term CME in different places. These are massive solar plasma ejections, literally billions of tons of plasma, and it also often has strong enhanced magnetic fields. And it kind of generates a strong shock wave in space, but these are slow, typically less than 1,500 kilometers per second, which is 900 miles per second, and take 2 to 5 days to reach Earth. Now, I wouldn't normally call something moving at 900 miles per second slow, but compared to traveling at the speed of light, it's slow. I also learned just a couple of days ago from a discussion that the fastest solar storm to ever reach Earth was in 1972, at least that we've recorded, of course. In 1972, and it only took 14 hours. So it was traveling really fast, and that meant it was really strong and was quite severe. So these are usually the ones that cause the most trouble. And they cause geomagnetic storms on Earth. They can also cause radiation storms. And well, I'll get there in a second. We are currently under a watch for a geomagnetic storm, by the way, later today. So the timing is good. Okay, so here just to show you, we have, these are coronal holes. These black regions are literally holes in the corona of the sun, and they cause fast solar wind. The solar flare is just radiation being radiated from the sun, and most likely in the center of this is a sunspot region. And then we have a CME, which is just a big blast of hot plasma from the sun, billions of tons shot out into space. And it's kind of like the sun burps, and if it's Earth directed, it can cause us some issues. So what happens when the solar wind, the interplanetary magnetic field reaches Earth? Well, we'll talk about it in more detail here in a minute, but the Earth has its own magnetic shield here, its own magnetic field. So in this diagram, the sun is on the left, the solar wind is flowing to the right. It hits the Earth's magnetic shield and it's deflected away, hopefully, under most circumstances. And it doesn't cause any major disruption. And this happens all the time under normal circumstances. The normal solar wind doesn't really cause us any major problems. But let's talk about the Earth's magnetic field for a minute. The Earth's magnetic field is called the magnetosphere. I was kind of surprised to see. I just happened to watch an episode of how the universe works on, I think it's the Science Channel, referred to as the magnetosphere. And I kind of wondered about that. And it's like I was reassured that the experts in the field all call it the magnetosphere. And if you refer to it as the magnetosphere, it means that you don't really understand what's going on. So anyway, it is the magnetosphere. And it protects us from the solar wind, just as that diagram showed. If we didn't have the magnetosphere, the Earth would be much more like Mars. By now, the solar wind would have blasted away most of our atmosphere. It would have eliminated all of our surface water. And we probably wouldn't be having this presentation because we probably wouldn't be here. Now, not to worry, but the one thing to remember about the magnetosphere is it has a north polarity, with field lines moving from the Earth's south pole to the north pole. So what that means is, we go back to this diagram, the Earth's magnetic field comes from the south pole, it goes around, it comes back to the north pole. So it's basically up in this diagram. And everything north-south in space is referenced to the Earth's poles, because there really is no north and south, and there really is no up or down in space. We just have to reference it to the Earth to keep things straight. So anyway, if you think about this diagram, the polarity of the magnetic field is up in this diagram, or north. That's all you really need to remember about that at all. And the solar wind, the interplanetary magnetic field, also has dimensions to its polarity. Now, if you think about it, the solar wind is a bunch of charged particles moving at a high rate of speed. You can almost think of it like a current, and an electrical current will generate a magnetic field. So it's generating the interplanetary magnetic field. Now, we don't care about the other two components of it. The one component that we do concern ourselves with is known as B sub Z, and it's either up or down. So if you think of the Earth's magnetic field normally, well, always being up, B sub Z either is up or down. So if it's up, it has a north polarity as well. So the Sun-Earth interaction. The solar wind always impacts the magnetosphere. I mean, it's constant. It's not constant, but it's continuous all the time. It never stops. And it usually also has a north polarity. So conveniently for us, the solar wind has a north polarity. The Earth's magnetic field has a north polarity. And if you think about two bar magnets, if you try to put the two north poles together, what happens? They repel each other, right? So just like the two bar magnets repelling each other, if the polarity stays north, the solar wind is just deflected around the Earth's magnetic field. So it doesn't really cause us any problems. We get fast solar wind or solar storms, CMEs hitting. That's when we have the largest impact from the solar wind. And so if it's fast enough or hard enough, it can compress the magnetic field. But if the polarity stays north, it still doesn't typically have a huge impact unless it is really strong. which is very rare. However, at times during a CME or a solar storm, or even during a fast solar wind from a coronal hole, the polarity will shift to the south. And when that happens, you can think of two bar magnets again. If you take a North Pole and a South Pole, they're attracted to each other. And if the polarity shifts to the south very much or for very long, a connection is made and a lot of energy is injected into the Earth's magnetic field. And a lot of that can end up into the ionosphere as well. So, it can disturb things. And when that happens, the most obvious effect again is aurora, but it can disturb the ionosphere severely as well. So again, it can be bad for propagation if we should get a storm. And Aaron, this would be a good time for you to do the keyword exercise.
Oh, okay. Yeah, we'll get right to it. Store prize time. So for those that are just joining in for Mentorfest this afternoon, the door prizes. Oh yeah. So we got another door prize opportunity here. Uh, we are going to open up the entry form, and the link to that is in the YouTube video description below. It's also on the section webpage, arrlntx.org. Just click on the Mentorfest in the banner at the top, and that'll lead you to the entry form. It'll be open for 10 minutes. And to help verify that you're here at the session right now, we need you to enter this key phrase, solar flare. So go ahead and enter that as the key phrase when you're putting in your entry. I've started the 10-minute timer now, and once the 10 minutes are up, we'll close, and at the end of the session, we'll announce who the winner is. So thanks, Dan. Back over to you.
Okay, great. Thanks, Aaron. And okay, so that's the Sun-Earth interaction. So HF propagation impacts. Okay, we have a lot of things here that are rated levels 1 to 5. Geomagnetic storms are the most common thing you'll see. Right now, we're under a watch for a G2 geomagnetic storm. The weakest being G1, the worst being G5. So this is just a moderate geomagnetic storm. Supposed to hit, their forecast, I think, is for roughly about 7 p.m. Central Time tonight, with a plus or minus there of a significant amount. And they're also not really sure about the severity of it. It might only end up being a G1. There's a lot of questions around it. So sometime probably between 7 o'clock tonight and sometime by mid-morning tomorrow, we'll probably have at least a G1 geomagnetic storm going on of some sort. It won't be great for radio, but it won't cause any other problems. There are no radio blackouts associated with it, but radio blackouts are rated in levels R1 to R5. And radiation storms, or no radiation storm associated with it. Those are levels S1 to S5. But these storms can severely affect satellites, can disrupt GPS, can even affect the ISS. If we have a high-level radiation storm, there are actually areas on the ISS that are considered to be shielded areas where the astronauts would go to wait out the radiation storm to protect them, hopefully from the radiation, because they are exposed to an extent, even though they're well within the Earth's magnetic field. Now, the one positive takeaway sometimes, no guarantees whatsoever, but sometimes as the disturbance settles, because the ionosphere did get energized and disturbed, it can enhance F-layer propagation. So sometimes we get a benefit on the backside of these storms, but you never know. But it's worth checking out if you have the opportunity. Just briefly talk about solar observation. We now have multiple probes that are closely studying the sun 24/7. We did lose the backside view of the sun. For a while, we had craft that were positioned there. One of them died, stereo B, and the other one, stereo A, and because of its orbit is quickly moving toward Earth. So in a couple of years, it'll show us the same exact face of the sun as we see from here. Not very useful at that point, but they do monitor the sun a number of different ways. we need to realize that we have basic sunspot data that goes back about 400 years. It's pretty crude. It's questionable accuracy, but we do have some indications going back that far. Now, the detailed data has been collected for about the last 75 years, and that data has been helpful in trying to predict what's going on with the sun. And you may not be aware of it, but there actually is a Space Weather Prediction Center in Boulder, Colorado, and it's run by NOAA and the National Weather Service, and it puts out a daily forecast for space weather. And you can visit their website. There, I have the link there. They have a lot of information there. They have a lot of data from the probes monitoring the sun, and it's an interesting read if you have the time. But just know that they actually do try to predict that now, because we have so many satellites up there, plus the space station and everything else, that it's important to know what's going on with the sun on a regular basis. So what do we care about? Okay, we're finally getting down to the crux of it. Okay, with that background, thank you for bearing with me. Now we get down to the nitty gritty of what we really are interested in, right? How does this affect propagation? Well, these are the factors that I think you should pay attention to. First, the solar flux index. What the heck is it, right? It's a measure of emissions from the sun at 10.7 centimeters, 2,800 megahertz. That frequency was picked really as a result of World War II. There was a lot of surplus radar equipment from that time, and that was repurposed to monitor the sun, and they just stuck with that frequency. But it's a fairly optimal frequency, and it's a good proxy for solar activity. So when you look at the numbers, the theoretical minimum is about 65. And sadly, during this last solar minimum, we came very close to 65 number of times. So we were pretty much at the bottom as far as solar activity is concerned. But the higher, the better for propagation. Now, as I recall from the last solar cycle, the highest number I recall seeing was 190. And I can tell you that when the solar flux was 190, 10 meters was open all day. You could pretty much count on work in Europe in the morning and work in the South Pacific in the evening. And it would just kind of go around the compass point during the rest of the day. So it was a lot of fun when it was that high. So let's hope that we get some higher numbers here soon. The other really good indicator is the sunspot number. Now, it's a little misleading because I want you to understand that this is not actually the count of individual sunspots. Each group counts 10, and then each individual sunspot counts 1. So you go from 0 sunspots to 11 sunspots. You never have anything less, because if you have 1 sunspot, you also have 1 sunspot group. So you now have 11. Right now, at the moment, we're at 29. So we actually have 2 groups and we have 9 sunspots. So that's just the way that number works. But again, the higher the better, root for sunspots. The planetary K index is another indicator. The range is 0 to 9. And this is a measure of the stability of the Earth's magnetic field taken every 3 hours around the world. 3 or less is best for radio conditions. Greater than 7 indicates the possibility of auroral propagation. We probably have a major storm going on. And propagation other than for maybe aurora, which we're a little too south for the most part, probably isn't all that good. So 3 or less is what we normally like to see. The planetary A index is a 24-hour measure of the stability of the Earth's magnetic field. And it's nothing but a weighted average of the previous 8 K index values. And again, lower is better. And we'll talk about a little more of that here in a minute. The solar wind speed, or SW. The normal solar wind is less than 500 kilometers per second. If it's faster than that, it indicates there's some kind of a disturbance, a coronal hole, a solar storm, something. B sub Z, we talked about that before. That's the the important polarity of the solar wind and the IMF. And a positive value means a north polarity, and that's going to be deflected by the magnetosphere and be pretty harmless. A negative value indicates the south polarity that will connect and energize the magnetosphere and in turn disturb the ionosphere. And finally, MUF, maximum usable frequency. Most of you are probably familiar with that. No big deal. It's just an indicator of the highest frequency that may be open. It's location specific. So conditions may be better or worse at your location. Just gives you a relative indicator of what bands might be open and how good things are. And it's nice to know that you can track all of these things with what I call the Solar Widget. Now, many of you, if you ever spend any time on QRZ.com or some other amateur radio websites, you may have seen this before, and you may have wondered, what the heck are all these numbers about? It's a very busy little graphic. And N0NBH keeps this updated, and it broadcasts out to all the sites that use this. And you can even, in fact, you can even get a gadget that goes on your desktop that will display this and update every 15 or 30 minutes to show you what the current conditions are. And if you look at this closely, we'll just go through this briefly. Up here at the left, at the top, you see SFI, or Solar Flux Index. Back then, it was a wonderful 174. I'd love to see that again, which is great. The Sunspot number was 88. The K index was 3. You don't have to worry about the 27 nanoteslas. And the A index was 4. Now, what that tells me, because this is the weighted average of the last 8 K index values, K just recently jumped to 3 because it was much lower for a long time before. So it was probably 0 or 1. You can ignore a lot of this stuff. It doesn't really matter. You get down here to the bottom, though, here's B sub Z. It's a positive 6.6, so that's good. Means the polarity is north. If it should shift, if it goes negative, this will change from green to yellow. And if it goes really negative, it'll change to red. The same with the solar wind. It's at 338.9, so it's less than 500. That's a good indication. It's normal. If it gets above 500, it'll turn to yellow. If it gets above about, I think it's 700, it turns red, saying it's really fast. So all those numbers are captured here for you, and you don't have to chase them down. You can find them easily here. If nothing else, going to QRZ.com and looking. Don't have to worry about this middle box much. It's not very useful. Most of these band conditions, if they're of any value at all, are in Europe. This is sporadic E for in Europe, so you don't have to worry about that. And the only other thing to point out is over here on the right, here's an MUF for Boulder, and it showed that it was 28.29, so 10 meters might have been open. And it shows relative band conditions up here at the top. Take those with a grain of salt. But all the numbers that you need to look at are captured in one place, and it's a very useful thing to just check on. It'll give you an indication as to whether conditions are disturbed or whether they're normal, or whether, hey, we got a bunch of sunspots and it's good. Now, for a better explanation, if you're an ARRL member, and hopefully you are, if you go to the ARRL website and go to the QST part of it, if you pull up the February 2014 issue of QST on page 78, there's a 2-page article that gives an excellent explanation of all these parameters, far better than I could ever do. And I would suggest that you pull that up, print it out, and keep it as a reference, especially until you get familiar with a lot of these numbers. And it also explains all these other ones that I didn't cover, just what they are, even though I don't think we care about those for the most part. But it's a great reference, and hopefully you'll be able to pull that up. And if anyone has real difficulty getting access to that, feel free to shoot me an email. I'll try to get you a copy of it somehow. So anyway, that's a great reference to have. Another great reference, some of you may know her, is the Space Weather Woman, Tamitha Skov. Her call is WX6SWW. She does weekly or sometimes more frequent space weather forecasts. They're her full forecasts are typically about 10 minutes long. They're kind of very much like a normal weather forecast. It's kind of like watching the Weather Channel for space weather. And she has literally been instrumental in raising awareness of the importance of space weather, not just within the amateur community, but in the general community as well. But she has a lot of connections in the amateur radio world. She just got the technical award for from the Dayton Hamfest from this year, which didn't happen, but they still gave their awards out, and she's done a tremendous job trying to make it familiar with space weather. And quite honestly, if you just watch her forecasts, you will learn without even realizing it, the terminology. So it's a great thing to just check out. If you ever watch the Ham Nation webcast, she typically does a weekly space weather forecast for them as well. And if you want to check out her stuff, she has a YouTube channel, very easy to find. If you search Space Weather Woman, it'll pop up all of her forecasts. She teaches mini courses on about a monthly basis for her patrons on Patreon. And she eventually publishes those as well on YouTube. So you can sit through her courses and learn a lot about space weather if you're so inclined. But I would definitely recommend that you check her out and watch her forecast because they're very helpful. So with that, let's get down to what we really care about, right? You know, what's going to happen with cycle 25? And of course, nobody knows. But quite honestly, the forecasts run the gamut from poor to awesome. I just saw one paper that just came out this last month that said, this gloom and doom that they came up with a different way to calculate what was going to happen, and things are going to be really bad. And it's going to be bad through cycle 27. You know, we aren't going to see any good sunspot cycles until after 2050, which is kind of depressing to me because I won't be around if that really is true, but I'm not sure that it is. The official NOAA forecast, also NASA joined in as well, is to be essentially a repeat of the week cycle 24 we just finished, peaking at 115 sunspots in 2025. Now, there was a group led by Dr. Scott McIntosh from the National Center of Atmospheric Research, who published a paper looking at different cycles, 270 years of data, and they concluded that it's going to be a much stronger cycle. It's going to ramp up faster than average, peak at about 250 sunspots, and it's going to happen in 2024. You need to realize that Dr. McIntosh is considered to be a bit of a maverick. He likes to shake things up, and he's considered a little bit out of the mainstream, which is a role he clearly embraces. I watched a recent update of his about a couple weeks ago, and he's still confident that cycle 25 is going to be above average. So we will see, and it's just a matter of time before we know. So things to watch. Okay, the north and south hemispheres of the sun have linkages, but they act independently. Cycle 24 was a weak cycle because it was a double peak cycle. The north hemisphere peaked first, and the south peaked 2 years later. So in order to get a high single peak, it requires the two hemispheres to be pretty much in sync. And so far in cycle 25, the south has been active, but the north is still struggling to get out a minimum. So in order for the McIntosh prediction to happen, you need to know that the north not only needs to awaken, but it needs to peak by roughly 2024. If it peaks later than that, we'll probably have another weak double peak cycle. Now, some of you may have noticed last November, it was around Thanksgiving time, I think, there was a big spurt of activity that got everybody excited. We had a high sunspot number. Solar Flux jumped above 100, and everybody was excited that the new cycle was kicking off and it was going to really ramp up. And then come early December, it all died. So that the conclusion now is that was just an aberration and wasn't an indicator of really anything. So right now, all I can say is stay tuned. There's some data that suggests that activity should ramp up in the next 3 to 4 months, according to Dr. McIntosh. But he just tweeted something last week that suggested that he's seeing things now that suggest it may only be a few weeks rather than months. So we may see a spurt of activity where we get a lot more sunspots quickly, and we just have to wait and see, I guess. But the quicker it ramps up, the better the chance of having a really good solar cycle. And that would be excellent for DX propagation and excellent for some of the expeditions and efforts they got planned coming up here in the next year or two. So here we can look at the past solar cycles. Now I can show you here clearly what I was talking about. As you can see, as we got down, this is cycle 24, and you can see that was much lower than the previous cycles. And it clearly had a double peak. The north peaked here and the south peaked here, and there was this big gap in between. And so if these two had coincided, it would have been a much better cycle. Now, the curve on the right are the predictions. The blue line here is what NOAA is predicting. The green line is what the mean would be going back to 1750. And the red line is what the McIntosh group is predicting it will be. So there's plenty of room there for variation as to what's going to actually happen. And right now we're here very close to the beginning of it, so it's hard to tell based on sunspot numbers just where this is going to go. And we'll just have to wait and see what takes place. So the ultimate takeaway from this I'll leave you with is that, regardless of analysis and predictions, the sun's going to do as it wants. You got to realize the sun's 4.5 billion years old. We have the best 400 years worth of data. And with that kind of time frame, any prediction that can be made is essentially based on a single data point. So let's just cross our fingers and hope that Dr. McIntosh is right. And with that, I guess I'll open it up for any questions.
All righty, thank you, Sid. Yeah, I know folks on the traffic nets are just waiting for the bands to get better. So come on, son. Oh yeah, one question from Steve Lott is asking, during poor sun cycles, are the low bands, as an 80 or perhaps even a 160 meters, are they better for DXing for long distance communication?
Yes, normally they are. I thought it was interesting that there was a discussion a couple years ago about 40 meters acting strange, in that it was sort of acting like 20 meters would, and it was kind of odd that during a solar minimum that it was doing that. And it was decided that, one of the things that I didn't talk about that the solar wind protects us from is the cosmic rays from galactic cosmic rays from outside of the galaxy even, which are high energy particles that come in, and they're bombarding us all the time, but the solar wind tends to protect us from that. The solar wind was pretty weak, the sun was quiet, and so when you have a solar minimum, you get more penetration of cosmic rays. And it was suggested that the cosmic rays were energizing things, and actually we were getting enough of that it was disrupting the propagation on 40 meters a little bit, but it wasn't bothering 80 or 160. But yeah, if you're a low band DXer, the solar minimums are your time in the sun. But for the rest of us who prefer the higher bands and don't have the room for the antennas, why we like sunspots.
Well, the antenna's only got to be 160 meters long, right? If you want it to be the actual, I mean, we all have room for that, right? No.
Well, I'm waiting to put up my dipole for 2,200 meters myself.
Oh, we have a interesting question that just came in. Total solar eclipse over the Dallas-Fort Worth Metroplex in 2024. Are there opportunities for amateur radio that day? In other words, does a solar eclipse affect amateur radio at all? Any thoughts on that?
Yeah, it's more than thoughts. what is it? The Hamsai group, if you're familiar with them. During, there was an eclipse, what, 4 years ago, that went through the middle part of the country. And I actually went to Missouri to view it. It was amazing. Um, but there was an effort to check that out. And basically they found that in the path of the eclipse, it acted like night. I mean, it literally, the low bands popped up briefly and had better propagation. So yeah, there's an opportunity. In fact, I'm sure there'll be an exercise too if you want to participate. Stay tuned for that. Sorry, I think my allergies are catching up to me. But yeah, it does affect propagation. Of course, it's fleeting because it's moving pretty fast. But they've studied it a couple times now. I think they actually had another event in South America with an eclipse. They were going to study data as well. So it's a fleeting thing. But quite honestly, if you're here in North Texas, I wouldn't be on the radio. I'd be out wanting to catch the eclipse because it's an amazing sight if you've never seen it.
Yeah, I haven't. I'm waiting for 2024. I'll wait patiently at home.
The scary thing about 2024 is it's in April, and there's a real possibility that the day that there's the eclipse, it could be like yesterday, and you won't see it.
An eclipse and severe weather.
Well,
for those in Texas and around, you know why we're laughing at that.
Yeah, I mean, you can discount the severe weather, but clouds alone are enough of a problem. In fact, when we viewed the eclipse in Missouri in 2017, I scouted out 3 different locations because I was ready to go and drive to get away from the clouds if it was a problem. But thankfully, it wasn't at all. It was good, clear skies. So it was an excellent thing, and it's really you just can't describe what happens when you get into total eclipse. It's just really strange.
Alrighty, well, we don't have any other questions in the chat. So, Stan, I know I've seen the little include the iframe thing for space weather, and it's like, well, how do they figure that out? Or for folks that are like, how does the sun really affect us? We all talk about the sun. This is really informative for me. I hope others found it really helpful too. And Stan, thank you much for joining us and giving us a lot of details on how the sun affects amateur radio.
Yep. Well, my pleasure. I hope everybody found it interesting. So thanks for having me.